Alright, these are your notes for section 10.1 on graphing exponential functions. We've already looked at how to solve an exponential equation and how to write an exponential equation given the y-intercept and a point, and in this video we're going to learn how to graph exponential equations, which isn't that difficult. It's pretty simple. It just requires a little bit of work. Okay? A couple things we want to remember. The general form is y equals a times b to the x. Your rules. A cannot be 1. Sorry, A cannot be 0. B cannot be 1. That's what I was thinking. So A can't be 0, B can't be 1, and B has to be positive. Can't be negative. Alright? Now there are two types of exponential functions. There are growth functions and there are decay functions. Alright? It's a very easy way to tell the difference. For growth, what you want to look at, here's the graph for growth. It starts out small and then it grows as it goes to the right hand side. Okay, it gets larger. Whatever your values, your y values will get larger as your x values increase. Okay? Now what you want to look for in a growth problem, that sounds bad, in a growth exponential problem, is that b is greater than 1. Okay, if b, remember b has to be positive and it can't be 1. So if b is greater than 1 in your form, that means it's an exponential growth problem. Okay? Now, common mistake is people think if b is greater than 1, it's growth. Well, if b is less than 1, it's decay. And that's partly true. But remember, b can't be negative. So b has to be between 0 and 1. It needs to be some decimal or fraction that's between 0 and 1, because again it can't be negative. Now our decay graph looks like this. It goes the opposite. As it goes to the right, the values get smaller because it's decaying. So we start out with a large value, and as we go to the right, as it continues in time or whatever we're talking about, those values get smaller. Here's some examples, common examples you'll see in this particular section. These examples say to classify each as growth or decay based on the equation. Alright? So let's look at this first one. The first one is y equals 0.7 to the x power. Now remember, a is out in front and b has the variables. So a here is 1 and b is 0.7. We said for growth, b needs to be greater than 1, and for decay, b needs to be between 0 and 1. Well, 0.7 is between 0 and 1, so this is a exponential decay. Okay? Pretty simple, just classifying them. Our second example, y equals 0.5 times 3 to the x. Well, again, a is what comes first, b is what's got the variable. So a is 0.5 and b is 3. A doesn't matter here. We're not looking at A. We're only looking at B. And B is 3. 3 is greater than 1. That means this is growth. Common mistake is to go off the 0.5 and say it's decay. Make sure you're going off what the variable, what the exponent is with. Third example. Y equals 10 times 4/3 to the x power. Based on looking at this, common mistake, people say, oh, it's a fraction. Fraction means it has to be between 0 and 1, so this is decay. They're wrong because 4/3 is a fraction that's greater than 1. It's an improper fraction. So since our fraction is greater than 1, this is a growth. Fourth example here is a little tricky. This fourth example says y equals 2 times 4 to the negative x. We can't have a negative exponent. So what we're going to do, kind of like what we did in the last video with our fraction, we made a negative exponent. We're going to do the opposite. We're going to make this exponent positive. To do that, we have to make it 1/4 to the x. What's in the parentheses is going to flip, so 4 becomes 1/4. Now my exponent's positive. So our new equation is y equals 2 times 1/4 to the x. This fraction is between 0 and 1. So this is a decay. Okay, so watch that. It's a common type of problem that they'll throw in there to make you think. So pay attention for a negative exponent. Last example here says y equals negative 2 to the x power. Now remember, a is out in front. It's not written, but it's understood that it's a 1. And then b is negative 2. Remember our rules. B has to be positive. Okay? If b is not positive, it's not an exponential. So this one's actually neither, because it's not an exponential function because it doesn't meet our rules. Okay? So pay attention to b. Remember, we're only basing growth and decay off of b. Doesn't matter what a is, but you do have to watch the exponent because it might make you flip a number or flip a fraction. Okay? So those are pretty simple. Those are just classifying growth and decay problems. Now, the next part here, we're actually going to graph an exponential function, and there are 4 different types of graphs you can have. We can have the growth graph, like I showed you, and we can have the decay graph. Okay, so this is growth. This is decay. Now, these are exponential functions, but they're not growth or decay. So exponential, not growth or decay. The reason they're not growth or decay is because a is less than 0. A is negative. Alright? When a is negative, we don't have growth or decay anymore. And we'll talk more about this in 10.6. But a has to be positive for it to be growth or decay. So here, these first two, a is positive, yes, those are growth and decay graphs. The other two, they are exponential graphs, but they're not growth or decay because they're below the x-axis. Okay, a is negative. Alright, so keep that in mind as you graph these. Now, we're going to talk about a few things. Okay, first thing that's not on here is an asymptote. And that's going to be important. What an asymptote is a boundary. Okay? It's a line that a graph will never cross. It's going to get really, really, really close to it, but it will never cross. And for all of these graphs we have, our x-axis is our asymptote. So if we look here, here is our asymptote. Okay? My graph gets really, really close to the x-axis, but it's never going to cross that. And all of our graphs are going to have that. All of the graphs will have an asymptote that's an x-axis. Now, as we go on and we learn more, the asymptote may not be the x-axis. But for this particular section, the asymptote's always going to be the x-axis. So our graphs should never cross it. They'll get really, really close, but they'll never cross the x-axis. The domain for any exponential function doesn't matter. As long as it's exponential, doesn't matter values for a and b, as long as it's exponential, is always all real numbers. Alright? And remember, if we want to write that in set builder notation, we can abbreviate it x, that funky E, and an R with 2 lines. That's way back a ways when we learned this. But we can say XER, means the same thing, means all real numbers. Our range is different. Our range is whether it's above or below the x-axis. Okay, so remember those graphs I showed you where we had 2 graphs above, and 2 graphs below? That dictates what our range is going to be because our graphs will never cross the x-axis. So, if a is greater than 0, if a is positive, our range is all positives. All positive numbers. We could say y, e, r with a plus. Okay? All positives. That's above the x-axis if we're looking at a graph. All right? If a is negative, then it's all negative numbers. Remember, a can't be 0 because that will cancel it out. So really we are talking a greater than 0, a less than 0. We could write it y, r with a minus. That tells us it's all the negative numbers. And this one is below the x-axis if you're looking at a graph. Okay? So a lot of information there. Domain, always all real numbers. Range, if a is positive, it's all positive numbers. If a is negative, it's all negative numbers. And remember, we've talked about this before. The y-intercept is always 0a. So what we're going to do is we're going to graph this function, this exponential function. We're going to give the domain, range, and y-intercept also. Okay? And it will help us to classify it if a is positive as growth or decay so that we can see if our graph meets the requirement that I showed you earlier, that it looks like that same shape. So let's start with the domain. Domain for any exponential function, always all real numbers. Okay? So XER. The range. Well, we look at A. A is positive. So it's YER plus. Okay? Y equals 2 times 3 to the x power. 2 is A. A is positive. So it's all positive numbers. Our graph should be above the x-axis. Our y-intercept, remember it's 0a, so it's going to be 0, 2. Alright? Now since this is above the x-axis and a is positive, we look at b now. B is 3. This means it's going to be growth because b is greater than 1. Alright? And a was greater than 1. Now what we do to graph this is we make a chart. We're going to make an XY chart, not an XX chart, an XY chart, and we need to have 5 sets of points in there. We're going to graph 5 points to do this. The one in the middle should always be the y-intercept. Okay? And then we need 2 above and 2 below. 2 greater x's and 2 less x's that are less than. So most of the time we use 1 and 2, negative 1, negative 2. We can always use those 5. Okay? Always use negative 2 through positive 2, and we've said that before. So use those 5 values for your graph. Now what we do is we plug them in. We're going to get values, and then we're going to plot our points. Let's start with 1. So it's 2 times 3 to the first power. Well, 3 to the first, sorry, because you got to do the exponent first, is 3, and then times 2 is 6. So there's that value. Now we would do 3 to the second. Do the exponent first, so 2 times 3 squared, which is 9, and we get 18. When we go smaller, when our exponents are smaller, 2 times 3 to the negative 1. Well, 3 to the negative 1 is going to be 1/3. So 2 times 1/3 is 2/3. So we ended up getting a fraction here, and that's okay, and I'll explain why in a second. For the next one, 2 times 3 to the negative 2, 2 times 1 over 3 squared, which ends up being 1/9. So 2 times 1/9 is 2/9. Now, the reason it's okay to have fractions here is because, remember, our values are going to get really, really close to the x-axis. So, as we go this direction, as our exponents get smaller, they get negative, they get closer to the x-axis. As we go larger, they grow, they get bigger. Now, that only works when it's a growth. If it were decay, it'd be flipped. When we would have the negative exponents, they would grow. And when we have the positive exponents, they would get smaller. Okay? So now we plot these. 0, 2 was our y-intercept. 1, 6. 2, 18 is going to be way up here someplace. Negative 1, 2/3. I'm going to approximate where that would be. And then negative 2, 2/9 be closer to the x-axis. Then we connect them. Remember, we do not cross the x-axis. Okay? It's the asymptote. And that's important. Okay? Now I've got another example here. What I want you to do is try this for class next time. You need to do that one on your own. It's the same thing. I'll get you started. I'll give you the domain, range, and y-intercept. Tell you whether it's growth or decay and all of that business. And then I want you to graph it on your own. Okay? Remember, the domain is always all real numbers. Our range depends on A. A is negative in this case, so it would be YER minus, because it's going to be below the x-axis. Our intercept, 0, -1. Now when it's below, remember it's not growth or decay, it can't be either one of those. So we're not going to say growth or decay here, but my graph should be below the x-axis. Alright? Should have nothing above, it should all be below. Now you need to finish, make yourself a table, and finish and graph. Alright? Try that one on your own. If you have any questions, go back to the example above. And if you have questions over anything we've done in the video, go back and watch the video. If you still have questions, bring them to class next time.